derived tau ij and had put tau ij in the normal stress tensor and had seen that the normal stress tensor was of this form. Now we will put this sigma ij in this equation, right? So uh, bear with me. So this will be rho duj by delta t plus rho uk k. Here I have mixed a k, right? Is equals to d sigma ij. I'll write the sigma from here, which is minus p delta ij plus lambda delta ij duk dxk plus mu dui dxj plus duj dxi, right? I think I've written it correctly. This entire thing was on a derivative, right? This one is only the sigma ij that I wrote. Plus, pardon my handwriting, rho fp. Now, this d by dxi, when multiplied by a Kronecker delta, will change its sign, will change the index. This will become minus dp by dxj plus lambda d of dxj duk by dxk plus mu sorry d of dxi. This will be xi because there is no Kronecker delta to change this index. Mu is the third bracket dui dxj plus duj dxi plus rho this thing, right? So this is the Navier-Stokes equation in the conservative form. We will simplify this equation and try to bring it in the form we are most used to seeing. Now we will talk about what this lambda and mu are. So we have this as sigma, right? We have we have defined this pressure as thermodynamic pressure. Thermodynamic pressure is the resultant of all motions, translational, vibrational, rotational, etc. All possible atomic motions gives rise to thermodynamic pressure. There is another pressure called mechanical pressure. Pressure, which is the resultant of only translation. This rises because of only translational motion. This is given as sigma 11 normal stresses. Right? Now, when we substitute, uh, when we find sigma 11, sorry, 22, 23, 33, the normal ones, from this equation, we can write it as sigma 11 is equals to minus p, because delta ij is 1 when I and j are same, and I and j both over here are 1, plus lambda d u1 by dx 1 plus twice into mu into du1 by dx1, because 1 1 1 1 both adds up and becomes 2. Sigma 2 2 in a similar way is minus p plus lambda du2 by dx2 plus twice mu du2 dx2. Actually this will be k only, because only I and j we are changing, k is constant. Sigma 233 is equals to minus p plus lambda duk dxk plus twice mu d. If we add these three and substitute over here, we will have plus uh, lambda duk by dxk plus 2 by 3 mu duk by dxk. It also becomes k because 1 2 3 and 1 2 3 over here gets added, and this is k. We will consider uh, the difference between thermodynamic and mechanical energies. Right, this is known as the second coefficient of viscosity. This is the normal coefficient of viscosity. dynamic viscosity, right? This can also be written as P minus, this is not a bulk viscosity. Now bulk viscosity is 0 for a special kind of fluid weight called Stokesian fluid or Stokes hypothesis. From Stokes hypothesis, it is told that bulk viscosity is 0, or these fluids are called Stokesian fluids, and is equals to, so uh, we will be considering fluids where lambda equals to 0, but to simplify this equation, where did the equation go? Here. To simplify this equation, but for all practical purposes we have compressible, incompressible fluids. For incompressible flows, where rho is equals to a constant, from continuity equation we have a duk by dxk equals to 0. Therefore this term will become 0, right? So we will consider this term. If mu is also constant, for constant dynamic viscosity, we can bring this part inside. So this will be mu into dui divided by d square ui dxi dxj plus d square uj divided by dxi dxi, right? Now these are interchangeable, so this one becomes mu d of dxj dui by dui, sorry, dxi, right? This again from continuity equation is 0, so only this term is left, right? Now this equation after the simplification becomes rho duj by dt plus rho uk by du dxk, right, equals to minus dp by dxj, this term vanishes, plus d, only this term remains, d square uj by dxi dxi plus rho fb, right? This becomes the famous Navier-Stokes equation. Okay, this can be written for j's as x, y, z, 1, 2, 3, right? So if we write it for Cartesian coordinates, here I have missed a mu term. Mu will be here. So in x direction, it will be du by dt, where u1 is u plus u du by dx equals to minus, sorry, plus v du, these are partial derivatives, right? Du by dy plus w du by dz is equals to minus 1 by rho dp by dx plus mu. See this k term will repeat 1 2 3. Again this I term will repeat 1 2 3. This will be d square u by dx square plus d square u by dy square plus d square u by dz square. Similarly, for y direction momentum equation, we have dv by dt plus v, sorry, u dv by dx plus v dv by dy plus w dv by dz equals to minus 1 by rho dp by dy plus mu d square v by dx square plus d square v by dy square plus d square v by dz square. It's my request that keep writing these equations so that you can memorize at least the Cartesian coordinate ones. Z direction dw by dt plus u dw by dx plus v dw by dy plus w These are the Navier-Stokes equations in the three Cartesian coordinates. Okay, thank you.